Good morning, everyone. First, let me introduce myself. My name is Mourad Rkhis. I'm a PhD student in Material Science and Engineering from National School of Applied Science of Eljadida. I'm delighted to talk to you about my contribution entitled Computational Study of Zirconium-based Intermetallic Hydride Substituted with Transition Metal for Hydrogen Storage Application. My talk is divided into four parts: background and motivation, hydrogen as energy vector, result and discussion, and finally conclusion and perspective. First, let me start with some general information. Since the 1860s, oil and natural fossil fuel have been the largest source of energy in the world. However, the huge demand of this energy induces what is called the peak oil concept, which said that we start to consume fossil fuel reserve. For this reason, scientific research has launched an ambitious program by the substitution of fossil fuel with renewable energy, but the problem is this energy does not ensure continuous production. So we have to develop new vector energy. But today, a very interesting energy vector, which is hydrogen, in correct way, dehydrogen. The hydrogen has many advantages: light fuel, not toxic, abundant on the globe surface, non-pollutant, and particularly a high mass density. But the problem is this hydrogen does not exist in the natural state and must be produced. So what is this method for producing? One of these methods is the use of electrolysis of water. This method is promising, but if we look at the industrial production, they use the steam or farming. To store this hydrogen, there is several methods such as compressed gas or liquid hydrogen, and the third method seems the most promising way for the future, which is hydrogen storage in solid state, with the different types such as intermetallic hydride, which are able to form irreversible bond with hydrogen. And among there is Zr due to its remarkable reversible absorption property. To investigate this material, the calculations have been carried out in the frame of the density functional theory (DFT) using several codes with some criteria for the convergence calculation. For a DFT calculation, we first start with the choice of the crystal structure of the system, then we perform a relaxation on the lattice parameters by varying the volume of the unit cell around the experimental value, to obtain the lattice parameter that minimize the energy. Now we can investigate the thermodynamic property by using these following equation. So according to this value of the formation enthalpy and desorption temperature, it indicates that this system has a high thermodynamic stability, and such stability should be reduced. This required to improve its performance. This suggests to replace zirconium with another transition metal, such as vanadium, titanium, iron, manganese, and chromium. So as a result, we found that when we introduce these elements, a slight variation of the lattice parameter leading to the contraction of the unit cell volume has been observed. And for the formation enthalpy, we found that the stability decreases linearly with a specific slope for each element, resulting in the enhancement of the thermodynamic property with a slight increase of the gravimetric capacity, which can be considered as advantage. In particular, each substitution element at particular concentration achieve an ideal formation enthalpy, which is minus 40 kJ per mole. In conclusion, let me sum up my main point. Density functional theory is a powerful tool for predicting the properties of material for hydrogen storage. ZrNEH3 has a high thermodynamic stability. Each substitution element in certain concentration appears to be the best substitution element. As a perspective, in the next work, we will try to reproduce the experimental side of these results. And that brings me to the end of my presentation. Thank you for your attention.